Hello there. In this video we're going to talk about a particular type of PDF known as an exponential distribution. For this type of distribution, you want to guarantee, if you decide to use it, that this random variable x satisfies a couple properties. The first of them must be that x must be a continuous random variable, or it can be nicely approximated as a discrete random variable by a continuous random variable, and the likelihood as x increases should decrease with it. So therefore, the probability that, say, let us assume x represents the time for something to occur, the likelihood that x is between, say, 2 and 3 hours must be less than the likelihood of being between 1 and 2 hours, and it should decrease as you increase the intervals of x, for example, right? So if it satisfies those two properties, then you may want to use an exponential distribution. There's going to be one parameter that you're going to be interested in, and that is beta. Beta is going to represent the average time that it takes for a particular event to occur. So this is almost, I guess you could think of it similarly to the Poisson distribution that we described a few videos ago. So of course the PDF for a exponential distribution is given by f of x is equal to 1 divided by beta, where beta is the average time it takes for something to occur, times e to the negative x divided by beta. And that's going to be defined on the positive real axis, and it's going to be 0 otherwise. Alright, so let's take a particular example. Let us assume that the average time a person watches a video online is exponentially distributed with the average watch time of beta is equal to 45 seconds, which is 3/4 of a minute. And let us assume you randomly select a person that is on this video watch platform, whether it be YouTube or something else. So there are some questions that you may want to answer. So let us assume we're interested in the probability that that person randomly selected watches a video for more than 2 minutes. So what is that going to be equal to? So it's already given that the average watch time is going to be equal to 45 seconds or 0.75 minutes. So let us make sure always that these are going to be in the same exact units so we don't get any errors there. So this is also the same thing as writing an integral form, the integral from 2 to infinity of f of x with respect to x. Now at this stage you should already be convinced that this function f of x is a probability density function. So that means you should have already verified, say, that the integral from 0 to some arbitrarily large number is equal to 1. So now let us assume we want to find the integral from, say, 2 to infinity. So let's go from 2 all the way up to some really large number. So that is going to be the approximation for the answer that we want. So it's going to be 0.060695. So 0.695. So the probability that a randomly selected person watches a video for more than 2 minutes is about 7%. So let us assume that a randomly selected person watches a video for less than 4.5 minutes. So this is again the same thing as writing the probability that 0 is less than or equal to x is less than or equal to 4.5. So we can easily write this in integral notation as the integral from 0 to 4.5 of f of x with respect to x, where x is time. So let's go from 0 to 4.5 to see what this is. So the integral from 0 to 5, so from 0 to 4.5, sorry, is going to be 0.9975. So 0.9975. So the probability that somebody watches a video within, say 5 minutes is almost guaranteed to always be true. So that's good. And let's assume that we're interested in the probability that somebody watches the video between 1 and 3 minutes. So this is going to be easily written in integral notation as the integral from 1 to 3 of our probability density function with respect to x. And we can use Desmos to calculate that. So that's going to be the integral from 1 to 3. So that's going to be 0.2453, so 2.53. And of course, keep in mind what you're actually doing here. So we have this probability density function that's given by this graph, and we're interested in the probability of x being between 1 and 3. So this answer here, 0.2453, corresponds to the area under the curve between 1 and 3. So remember that areas under PDFs correspond to the probabilities of interest. So let's do another example to illustrate the exponential distribution. So example 2. So suppose that the time it takes for a vehicle to warm up its engine is exponentially distributed with an average warm-up time of 3.21 minutes. And let us ask a couple of questions. So what is the probability that for a randomly selected vehicle, that the probability that its engine warms up within the first 2 minutes is equal to something, right? So again, the average time is going to be equal to beta is equal to 3.21, and always make sure that these times, or whatever you're measuring, is in the same exact unit. So let us go over to our exponential distribution and change our value of beta. So beta is going to be equal to 3.21. So this new curve is going to be our new PDF. And again, we see that the area under that curve is going to be equal to 1, which is good. So let us find the integral under this curve from 0 to 2. So that's the probability of warming up within the first 2 minutes. So that's going to be 0.4637. So 0.4637. So 0.4637. So that's going to be the integral from 0 to 2 of our probability density function. So let us also ask, what is the probability that a randomly selected car's engine warms up between 1 and 3 minutes? Again, we don't need to do any conversion since it's in the same unit. So again, that's the integral from 1 to 3 of our probability density function f. So the integral from 1 to 3 is going to be equal to what? 1, 2, 3. So that's going to be 0.3396. And keep in mind, if your statistics course is more calculus based, then these integrals should actually be very easy to find using your fundamental theorem of calculus methods. But again, we're only focused on the probability and applications of it in this series. So let's assume that the time it takes to warm up an engine is exponentially distributed, and let's assume we're interested in a randomly selected car's engine only warming up after 4 minutes. So of course, if you're going for efficiency for vehicles, you want this probability to be as low as possible. So that's going to be equal to the integral from 4 to infinity of f of x with respect to x. So what is that going to be? So that's going to be equal to the integral from 4 to infinity. So 4 to infinity. I'm going to let 10,000 correspond to my infinity. And if I add some zeros here, notice that this area does not change in accuracy. So 0.2876. So 0.2876 is the probability that a randomly selected car's engine doesn't warm up for at least 4 minutes. And that is pretty much a breakdown on how to use the exponential distribution to calculate probabilities of particular events.